this has been a day. I'm just telling you. It's a long story. They cleaned my room, and they just basically moved everything in and put it right there in the corner. And so this is much later than I expected. It's 10 after 6. I spent the last 2 hours putting my room away and trying to find stuff that is now missing. Okay? So primarily what is missing is the little adapter that goes from my iPad to the blue cord that allows me to run through the projector. For some reason, that's missing, and I have no idea where it is, so I'm just going to have to wing this a little bit. So just bear with me here. I have my iPad. Well, actually, if I had my iPad and it would run this PHeT simulation, we wouldn't be having this discussion either. So technologically, it's been a bad day, but we're going to make the most of it. All right. So one of the things that baffled scientists for a long time was what's known as the photoelectric effect. So what happens in the photoelectric effect, allow me to demonstrate, is you shine a light on metal and you have a certain intensity, okay? And what happens is that as you shine this light here on the surface, it kicks out electrons, and they go across, and you create a current, okay, which in this case is like 0.072 amps, okay? So to make this happen, they said, okay, well, what's taking place here? Because, and this is where you can't think about this too much, or you'll end up like in the corner in the fetal position sucking your thumb. Just accept that it works. So, and this goes down even into the argument, is light a wave or is light a particle? So fundamentally what has to happen, whether it's a wave or a particle, is that these electrons are in a bound state around the nucleus. They're happy there. Mother Nature's lazy. It's happy. It's cool. It's showing up. And then what has to happen is that whatever this energy is, as it comes in, it gives these electrons so much energy that they leave this metal plate, and then they create a current, and it comes over here, okay? So that was one of the first things they sort of said, okay, well, all right, well, what happens if we change the color of the light? Okay, so I'm going to change the color of the light, and I'm going to make that color of that light, I'm going to go from, instead of violet, I'm going to go down here into like orange, okay? So if I move it down here to the orange, okay, and the other thing you'll notice is that the wavelength has become longer, okay? So as you go from violet into red, the wavelength becomes longer. Now, if you remember, that's why we studied light first, as the wavelength becomes longer, the frequency becomes smaller and the energy becomes smaller. So, okay, all right, well maybe it's stopped, but maybe if we let it shine on there long enough, it'll be kind of like boiling water. So if we let it shine long enough, even though it isn't making it happen, well, maybe it sits there long enough, the electrons will eventually gain enough energy and they'll like boil off. What they found is that no matter how long they let it shine on that, it never started, okay? So it either happens or it doesn't, so time isn't a factor. So what that means, either these electrons either gain enough energy to leave that bound state, or they don't. So what you'll see is that if I go across here, is that if I make this shorter and shorter and shorter, down to 541, 524, okay? So if I'm at 524, what happens is that I'm beginning to get these electrons to be emitted. So if I'm at a longer wavelength with less energy, nothing happens. But there's a threshold that I can cross, and then I can begin to make these electrons begin to flow across, okay? Now, if I go to even a shorter wavelength, okay, then what you'll see is that we get more electrons coming off of here. So what they figured out is that there's a minimum threshold, but then as you go and you get more and more energy, basically what happens is that you were able to pull more electrons out of this metal. So that's one, there's going to be three variables that you can manipulate in this thing. One of those is your wavelength. Your wavelength determines the energy of the photons. So basically, and you'll hear this story in just a second. So what happens with that wavelength is that you come over here to this equation, and you should be able to see this if I got my camera right. I can't write on the board, thank you very much. But this is HF, this is what's on your equation sheet. So K max equals HF minus psi. This psi is your work function. This tells you how much energy it takes to get the electrons out. This is how much energy the photons bring in. So basically, if this is bigger than this is how much kinetic energy you have left over for those electrons to have. So here's the story that I'm going to tell. This will never happen, but let's just say, okay? So this is never going to happen. Keep this in mind. I don't want you to come back and go, oh, this is working. This is purely hypothetical. I know this is never going to happen, okay? But let's say that Cool-Tate ends up in jail. I know, shocking. Cool-Tate is in jail. And the judge says, I've posted your bond at $50, okay? So the $50 is like the work function, okay? That's how much money it's going to take to get Tate out of jail. Now, Tate doesn't have 50 bones with him, okay? It's coronavirus, he doesn't carry cash, okay? He doesn't have his credit card. So he's going, oh man, what am I going to do? So he calls Liza, okay? He goes, yo, Liza, I'm in jail, okay? And I got to pay $50 to get out of jail. Liza going, seriously, Cool-Tate, you're in jail? This is just too funny. Of course, she's texting everybody, Cool-Tate's in jail, okay? But Liza, being the nice person that she is, she's going to go help out Cool-Tate. So Liza shows up with $49.50. Goes to the judge and goes, looks up to the judge. Goes, hey judge, I'm here to free Cool-Tate. I'm really cute, I've got a cute dog, and I've got $49.50. Can I get Cool-Tate out? The judge says, no. I set the bail at $50. That's how much money you have to get Cool-Tate out. Cute as you are, and you can sit here and you can try and plead with me all that you want, but I'm not going to let you go. So that's what's happening when you have a wavelength that's too long. You have less energy than the work function. And no matter how long you shine that light on there, it doesn't make any difference, okay? So let's say that Liza shows up with exactly $50, okay? So she has $50. So that's how much energy she brings into the system, okay? This is the energy of a photon, or how much money Liza has. It's $50 to get Tate out. So this is cool, right? She frees Tate. She gets Tate out of jail. But unfortunately, they have no way to get home at this point. They've got no money, okay, because she spent all the money that she had to get Cool-Tate out of jail. It's like, really? Seriously? So, if they want to have some money left over to give some kinetic energy to call Uber and get a ride home, she's got to bring more than the $50. Okay, so Liza shows up with $60. Okay, so Liza shows up, she has $60. This is like the energy of the photon. She has $60. She's got to pay $50 of it to get Tate out of jail. That means they have $10 of it left over. Okay, so that's like that K max. So any energy above and beyond the work function is what's going to be left over that you can have as kinetic energy. Okay? So basically, the more money that Liza brings with her, the more K max that she's going to have. Now, Tate's a mild offender, right? $50, right? Not bad. So let's say that somebody else is in jail and they have a bail of, say, $200, okay? So if Liza shows up with $50, she can only get Tate out of jail. She can't get the people farther in that have posted bond of $200. She doesn't have that kind of money. Now, if she does show up with, let's say, $250, then not only can she get Cool Tate out of jail, she can get somebody else who's also further in jail who's got more money that has to post bond. So this is what happens when you get into more and more and more energy. You're able to free electrons that are closer and closer to the nucleus because they have more and more and more and more energy. So when you look at that value for that work function, okay, what you're going to find is that work function, and there's a table in your book, is that each metal has a different work function based upon how much energy it takes to free that most loosely bound electron. So when you look at that, you've got gold, calcium, magnesium, whatever, okay? All these different metals have different work functions based upon how much energy it takes to free them. Okay, so your wavelength determines how much money Liza brings. Now, we could talk about the intensity, okay? So the intensity is going to be the number of photons that are going to show up. So what I'm going to do is I'm going to increase the intensity of the light, okay? Now, what should, hold on. Now, notice when I lower that intensity, okay, that I'm not having as many electrons flowing across. I'm still having some electrons, okay? These photons are still striking the metal and carrying enough energy. But there's just not as many of them. So this is like you're trying to free, there's a whole bunch of Tates that need freed. You don't have very many Lizas showing up. You're not getting very many electrons being kicked out. Now, if you increase that intensity, now you're going to get a lot more electrons being kicked out because now you're going to have a lot more of those photons showing up with $60. That's enough to get Tate out of jail. Okay, so the more intense it is, the more current that you're going to have because you're going to have more electrons being kicked out. Now, here's the third thing that you can manipulate. And let me go back. Let me go back, and I'm going to shove this over to that longer wavelength and stop it. Okay? Now, here's what they found. Is that at this point with this yellow light, I'm not having any electrons being kicked out. So that, well, maybe if we increase the intensity of the light, okay, we make it a really, 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 really bright yellow light, okay? So we're going to increase the intensity up to 100%, okay? Now, even if I increase that intensity to 100%, notice that I still don't get any current. So either that photon has enough energy to overcome that work function and kick it out, or it doesn't, okay? So no matter, if you don't have enough energy in those photons, here's what's important. No matter how intense you make that light, no matter how long you let that light shine on there, it's not going to happen. So there's like a threshold. So what they figured out, and this is actually where what Einstein did some early work on, and this is where the whole bunch of things come into play. Planck's constant, which is your HF, which gives you the energy per photon. So this is all done in the late 1920 or early 1920s. This was kind of the golden age of quantum physics because they were starting to figure all this out. So what they settled on, and this is where this gets extremely weird in terms of trying to conceptualize what's happening. So you have this electron orbiting the nucleus, going very, very close to the speed of light. And it's stable, okay? These are stable metals, magnesium, calcium, okay? Gold. And those electrons have been there for a long time, because especially you get into those heavier metals like gold and things like that. These were made in the collapse of neutron stars, okay? This isn't like, oh, you know, they just kind of willy-nilly kind of, you know, these have been around for a long time. They have been through a lot. They have been formed by the collision of neutron stars, okay? Very intense. And those electrons have stayed with them, and they're stable. They're going, hey, man, we've been a lot, okay? So all of a sudden, these electrons, which are moving very, very close to the speed of light, they're very stable. Along comes this photon. So this electron that's moving very, very close to the speed of light has an extremely small mass, somehow interacts with this bundle of light called a photon. So here's this photon going around, okay, extremely high speed. Photon hits it, and it gives it so much energy that it leaves its normal bound state and then comes over here and we can collect it as a current. So that's why I said, accept the fact that it works. We really don't know the mechanism, because this photon is just a bundle of energy. And then it interacts with this electron, tiny, tiny, tiny bit of matter. And it gives it so much energy that it leaves this surface and then becomes a current over here. So it's kind of cool, but don't think about the mechanism too much. Okay, so we shine the light, we get a current, this thing comes across. Good effect. Now, the next thing that they did is they said, oh, okay, well, that's clever. So let's get some flowing again, okay? All right, and so we'll kind of go into the blue range, okay, 463 nanometers. And then they said, okay, well, let's hook up a battery to it, okay? So now we've got this battery down here. And they said, okay, well, let's create some positive voltage, okay? Now, look what happened to these electrons. So you guys can't see this, but this side has become positively charged, okay? And this side has become negatively charged. Oh, right, these are electrons. So they're going, ooh, this is kind of cool. So not only are these electrons getting out, so at this point, Liza has freed Tate. They're free, Tate's free. Tate doesn't like being in jail, so Tate is being repulsed by the jail, as well he should be. And over here is like a McDonald's, right? And he hasn't had McDonald's in a long time. So this thing is busting out of here and hauling over here, because Tate is repulsed by the jail and he's attracted over here. Now, here's the interesting thing that happens. Okay, I'm going to go back to making that neutral. Okay. And I'm going to set that voltage back to, hold on, whoa. So notice I got a current of 0.036, okay? Now, when I increase that voltage to 3 volts, notice that my current stays the same, okay? That's going to be an important part. So all I'm doing is that I'm making those electrons leave that negatively charged plate and move over to that positively charged plate, okay? And they're going to have more energy because they're in an electric field, but I'm not going to increase the number of them. Now, interesting thing happens. If I take that voltage, though, and I make it negative, now, look what happens. If I make this a negative voltage, which means this is like the positively charged plate now, and this is the negatively charged plate. Now look what happens. So these electrons are kind of coming over here, and they're going, whoa, and they're going to stop, okay? Because at this point, Tate goes, you know, Joe wasn't so bad, you know. As they say in the trade, I got 3 hots and a cot, you know, 3 hot meals and a cot, okay? 3 hots and a cot. He going, you know, Liza, appreciate the fact that you got me out of jail, but I think I'm going to go back. So what's happening here is that if we can figure out that minimum amount of voltage it takes to stop the current, then we can work backwards and we can figure out how much energy it took. So it's like Tate is leaving with $10, okay? Tate. So here's the scenario. Liza showed up with 60. 50 bucks went to pay the jailer. Tate now has 10 bucks. So basically, if we can figure out how much energy it takes to stop Tate, so that he doesn't make it over to here, and in fact, we've got to pay, $10 worth of energy, then we know how much energy those had. So this is a situation where we can't directly see the electrons going. This is a nice visual, but when you see this, I don't want you to think that if we were to actually look at this, we could see these electrons moving. We can't. So here's the big idea. If this is positively charged, think about this in terms of the electrons. If this is positively charged, these electrons leave here, they're attracted to this positively charged plate, and they're repulsed by this negatively charged plate. So what that does is, this is what we could call the stopping potential. This tells us how much energy that we have to make these things stop. So basically, over here, that stopping potential tells us the K max. That tells us how much energy that we have. Now, at that point, when you get to K max, you can work in electron volts, you can work in joules, you can work in a whole bunch of different things. So I'm going to do some more work on my iPad, where I can actually write some things out and go over some problems. But I needed you to see this visual here. So anyway, so that's the story. And it's like 80 degrees in here, now it's 6:30, and I'm really hot and sweaty. So anyway, I'm going to shut this down, and there will be more to this.